Welcome to a journey across the universe, where we're going to explore the cosmic distance scale. This scale is a vital tool in the world of astronomy, helping us to comprehend the vastness of space. You see, the universe is so incredibly large, we need a unique way to measure it. The cosmic distance scale provides just that, offering us a method to gauge the unfathomable expanse of the cosmos. Understanding the distances between celestial bodies is not just about appreciating the sheer size of the universe. It's also fundamental to understanding the universe's structure, its history, and its very destiny. By grasping these distances, we can decipher the life cycles of stars, the architecture of galaxies, and even the expansion of the universe itself. So buckle up as we take a ride across the cosmos, understanding the scales that make it possible. Before we zoom off, let's understand the yardsticks of the cosmos. To comprehend the vastness of the universe, astronomers use several units of measurement. First up, we have the astronomical unit, often abbreviated as AU. The AU is based on the mean distance from the Earth to the Sun, which is about 93 million miles. This unit comes in handy when we're talking about distances within our solar system. Then we have the light year. Despite what its name might suggest, a light year isn't a measure of time, but rather a measure of distance. It's the distance that light, zipping along at about 186,000 miles per second, can travel in 1 year. So, when we say a star is 20 light years away, we mean that the light we see today actually left that star 20 years ago. For even greater distances, astronomers use the parsec, which is equal to about 3.26 light years. This unit is based on the method of parallax, a technique used to measure the distances to nearby stars. We'll delve more into the parallax in the next scene. Lastly, we have the megaparsec, used for measuring incredibly vast distances, such as those between galaxies. 1 megaparsec equals 1 million parsecs, or about 3.26 million light years. It's crucial to understand these units because they form the basis of our cosmic distance scale. They help us gauge distances between celestial bodies, allowing us to map the universe, study its structure, and comprehend its immense scale. Without these units, it would be like trying to measure the dimensions of your house with no ruler or tape measure. With these units in our toolkit, we're ready to begin our journey. Scene script. First stop, our neighboring stars. But how do we measure distances to them? Picture yourself on a long road journey. As you drive, the trees close to the road seem to move faster than the mountains in the distance. This apparent motion is called parallax, and it's not just a highway phenomenon, it's a principle that underpins our understanding of the universe. Now let's apply this concept to the cosmos. When we observe a star from two different points in Earth's orbit around the Sun, it appears to move against the backdrop of distant stars. This apparent shift is stellar parallax. It's tiny but measurable, and it's the key to unlocking distances in our cosmic neighborhood. Imagine drawing an imaginary triangle. The base is the diameter of Earth's orbit, and the two sides are lines of sight to the star at 6 months apart. The angle at the star is the parallax angle. The smaller this angle, the farther away the star. Simple geometry, right? But of course, the universe isn't quite so simple. Parallax angles are incredibly small, measured in arcseconds, a unit so tiny that 1 arcsecond is to 1 degree what 1 penny is to $10,000. And yet, with precise instruments, we can measure these angles and calculate the distance to stars up to a few thousand light years away. This method is so reliable that it's our first rung on the cosmic distance ladder, a series of interdependent methods for determining the scale of the universe. It starts right here, with the parallax of nearby stars. Let's take Proxima Centauri, our closest stellar neighbor. Its parallax angle of about 3/4 of an arcsecond tells us it's a little over 4 light years away. That's 24 trillion miles, in case you were wondering. Parallax, a simple yet powerful tool, brings the stars a bit closer to us. So the next time you gaze up at the night sky, remember that you're not just seeing stars. You're glimpsing the edges of cosmic geometry. Venturing further into our galaxy, the Milky Way, we need more tools. You see, our home galaxy is a bustling neighborhood, a swirling disk of gas, dust, and roughly 200 billion stars, including our own sun. Let that sink in for a moment. Now the question is, how do astronomers measure distances within this vast cosmic city? Well, one method in their arsenal is spectroscopic parallax. Although it shares a name with the parallax method we've discussed earlier, it's a different beast altogether. In essence, this technique involves analyzing the light spectrum of a star to determine its absolute brightness or luminosity. By comparing this with the star's apparent brightness as seen from Earth, astronomers can calculate the distance to the star. It's a bit like trying to figure out how far away a light bulb is by comparing its actual brightness with how bright it appears to our eyes. Another tool in the cosmic distance toolbox is variable stars, specifically a type of pulsating star known as a Cepheid variable. These stars pulsate at a rate directly related to their intrinsic brightness. This unique characteristic makes them excellent distance markers. By observing the pulsation period of a Cepheid variable, astronomers can determine its absolute brightness. And just like with spectroscopic parallax, they can then compare this with the star's apparent brightness to calculate its distance. The Milky Way is vast, with a diameter of about 100,000 light-years. That's a distance so enormous that it takes light, moving at its incredible speed, 100,000 years to cross from one side to the other. And yet, in the grand scheme of the universe, it's just a tiny speck. Within our galaxy, we're already dealing with distances that boggle the mind. But we're just getting started. From galaxies to the universe, our journey takes us even further. We venture beyond our immediate cosmic neighborhood, towards the expanding universe's outer limits. Here, we grapple with a groundbreaking concept, Hubble's law. Named after the astronomer Edwin Hubble, Hubble's law is a cornerstone in our understanding of the universe. It's a simple yet profound statement. The universe is expanding, and galaxies are moving away from us at speeds proportional to their distance. In other words, the further a galaxy is from us, the faster it's moving away. This law emerged from observations of galaxies' redshifts. When we look at distant galaxies, we don't see them as they are now. Instead, we see them as they were when the light we're observing started its journey towards us. This light is stretched or shifted to longer, redder wavelengths, hence the term redshift. The degree of this redshift directly relates to a galaxy's velocity. The more significant the redshift, the faster the galaxy is receding from us. But how does this relate to distance? Well, if we know a galaxy's velocity, Hubble's law allows us to calculate its distance. This is because the law establishes a constant rate of expansion known as the Hubble constant. By dividing a galaxy's velocity by this constant, we can estimate its distance. This is an essential tool for astronomers. It's like having a cosmic tape measure, stretching billions of light-years across the universe. With Hubble's law, we've stepped outside our galaxy and into the wider universe. And in doing so, we've found that the universe is not static. It's not even just vast. It's growing, expanding in all directions, carrying galaxies along with it. So the next time you gaze up at the night sky, remember, those pinpricks of light aren't just far away. They're moving, and the universe itself is growing. With Hubble's law, we've stepped outside our galaxy and into the wider universe. Now, let's turn back the clock and look at the early universe. To do so, we need to understand a fascinating phenomenon, the cosmic microwave background, or CMB. The CMB is a remnant radiation that dates back to a time when the universe was just 380,000 years old. It's like the afterglow of the Big Bang, providing us with a snapshot of the universe at its infancy. The CMB allows us to peek into the past, but it also helps us understand distances in the early universe. You see, when the universe was young, it was filled with a hot, dense soup of particles. As the universe expanded and cooled, these particles eventually formed atoms, which led to the release of the CMB radiation. This radiation has been traveling through space ever since, like a cosmic message in a bottle, and it carries with it the story of the early universe. By studying the CMB, we can learn about the size, composition, and future fate of the universe. But how does the CMB help us measure distances? Well, the CMB is not uniform. It has slight temperature variations, or anisotropies, which correspond to density fluctuations in the early universe. These fluctuations eventually led to the formation of galaxies and large-scale structures we see today. By studying these anisotropies, we can determine the scale of these structures and hence the distances between them. Moreover, the CMB is redshifted, just like distant galaxies. The redshift of the CMB tells us how much the universe has expanded since the time the CMB was released. This allows us to extend the cosmic distance scale to the farthest reaches of the observable universe and even to the earliest times. The cosmic microwave background, a snapshot from the past, helps us measure distances of the earliest times. It's our cosmic time machine, a way to voyage into the depths of the early universe and truly understand the grandeur of the cosmos. Our understanding of cosmic distances shapes our understanding of the universe itself. This statement is a testament to the role of precise measurements in cosmology, the branch of astronomy that studies the universe's origin, evolution, and eventual fate. When we delve into the cosmic distance scale, we're not just measuring physical distances, we're also measuring time, as light from distant objects takes years to reach us. In essence, looking into the cosmos is like looking back in time. We're witnessing events that happened billions of years ago, and this provides us with valuable insights into the history and evolution of the universe. Now let's talk about something that's been a hot topic in cosmology for a couple of decades now: dark energy. This mysterious entity, making up about 70% of the energy content of our universe, is believed to be responsible for the accelerated expansion of the universe. But how does it link to cosmic distances? Well, the farther away a galaxy is, the faster it's moving away from us. This relationship, known as Hubble's law, was one of the first indications of the universe's expansion. With more precise measurements of cosmic distances and the speed at which galaxies are moving away, scientists were able to deduce that this expansion is not slowing down, as initially assumed, but speeding up. That's where the concept of dark energy comes into play. Dark energy's exact nature remains one of the greatest mysteries in science. However, its effect on the universe's expansion is a key piece of evidence for its existence. By studying cosmic distances and the redshift of galaxies, cosmologists can estimate the amount of dark energy and its influence on the universe's fate. So, distances not only tell us where things are, but also when they are, and how the universe is changing. As we continue to refine our methods of measuring cosmic distances, we inch closer to understanding the universe's ultimate fate, an endeavor that's as exciting as it is daunting. Our journey across the universe comes to an end, but the exploration never stops. We've voyaged through the vast expanse of space, using the cosmic distance scale as our roadmap. It's a tool that allows us to quantify the seemingly infinite universe, enabling us to understand its structure and evolution. The cosmic distance scale is the backbone of cosmology. Astronomical units, light years and parsecs, these are not just mere numbers, but the language of the cosmos. They help us comprehend the incredible distances between celestial bodies and the vastness of the universe. We've learned how parallax, the apparent shift of an object against a distant background when viewed from two different positions, helps us measure the distances to nearby stars. This geometric method is the first rung on our cosmic distance ladder. We've also delved into the concept of standard candles, such as Cepheid variable stars, whose intrinsic brightness helps us determine their distance. Their periodic dimming and brightening offer us clues about the universe's far-off corners. We've explored Hubble's law, a revelation that changed our understanding of the cosmos. It showed us that the universe is not static but expanding, with galaxies moving away from us, their light redshifted due to this cosmic expansion. We've also journeyed within our own Milky Way, understanding different methods used to measure distances within our galaxy. And we've ventured beyond, using triangulation to measure distances to objects beyond our galaxy, facing the challenges that come with such deep space measurements. Finally, we've touched the cosmic microwave background radiation, a relic from the early universe, which provides us with insights into the infancy of the cosmos. In this journey, we've seen how the cosmic distance scale is not just a measure of space, but also of time, helping us peer into the history of the universe. It underscores the importance of ongoing research and advancements in accurately measuring distances in the vast cosmos. Remember, every star you see in the night sky is a journey waiting to be taken. Until next time, keep exploring.